So today we will continue analyze the heat exchanger. As we did last time, we were able to analyze this simplest concentric tube shell heat exchanger using log mean techniques. But however, in reality, in practice, in industry, most of heat exchangers are much more complicated than that. And then we have already introduced all kinds of exchangers like this. Like this is a single tube pass, and then a single shell pass. And then this one will be two tube pass, and then one shell pass. And then this one will be actually a 4 tube pass, and then 2 shell pass. So this is still a tube shell. These are all tube shell heat exchangers, but different paths. And then in addition to that, we also have cross flow heat exchangers. These are 2 types. And then within that, there's also different configurations in terms of whether or not the fluids are mixed or not. So anyway, so in order to analyze how good or how bad the heat exchanger performs their job, or how to design a heat exchanger to satisfy your requirement, that requires us to solve a so-called design or evaluation problems. So let's say we have design or versus evaluation. Or performance evaluation, or evaluation of performance. So performance evaluation. And then the way that we do it, we will use different parameters and then to correlate those. So there are a few operation parameters, such as the mass flow rate, right? And then the specific heats of the fluids, and also the temperatures, inlet, outlet, all these temperatures. And then in terms of the design of the heat exchanger, then there is also a parameter that is correlates to the design. So most of the time it's the area. So if for the design, we need to calculate area using the operation conditions. Of course, the fluids itself, the speciation of the fluids, what type of fluids it is. And then for the performance evaluation, it's opposite. So we will use area and also the overall heat transfer coefficients. Sometimes those are given as convection coefficients, and then you calculate the overall coefficient using these convection coefficients, right? And then in addition to that, we also have the mass flow rate, specific heat, and then however, most of T's, and then we can calculate the additional temperature. Most of time is outlet, at the outlet. So basically the performance evaluation is basically tells you that, oh, you have this heat exchanger, and here are the inlet condition. What will be the outlet temperature? In other words, how much heat it can be transferred across this heat exchanger. So in order to calculate that, we need to introduce a few concepts. The first one is the maximum heat that has been transferred across a heat exchanger in an ideal situation. So that will be the Q max. The Q max will depending on the 2 fluids. So the inlet temperature, the hot inlet temperature, minus the cold inlet temperature are the maximum temperature differences. And then in the in the maximum condition, you can only make one of the fluid to a new temperature that is same as the inlet temperature of the other fluids. So I'm just using this diagram to tell you. So let's say the hot and the cold, right? The cold and hot. The maximum situation will be if the cold eventually reach the hot inlet temperature, then no more heat transfer can happen, even if your hot one doesn't change. That's the maximum. Or in another condition is actually the hot fluid has been cooled down all the way to the cold temperature. And then after that, no more heat transfer can occur, right? So these are the two maximum cases that can be transferred, maximum heat that can be transferred. But between the two, which one is smaller? The smaller one between these two will be the true maximum of that heat exchange, or true maximum of that operation. So then, the amount of the heat the code will be increased, will be the MCHC delta C, right? This will be basically the maximum delta T. Possible. And then, however, between these two cases, this and this, the smaller one will be the true maximum. So between the hot and the cold, actually the smaller capacitance will be determining the maximum. So C minimum, the minimum total heat capacitance is the minimum between the two. The two are, need some space. The two are, first one is the cold one. The second one is the hot one. And then this will determine the maximum heat transfer. And then the effectiveness of a heat exchanger is defined as the ratio between the true heat transfer rate versus the maximum heat transfer rate. And then another concept, this is basically a performance of a heat exchanger. And another concept is defined as a number of heat transfer unit. Heat transfer unit, NTU, number of transfer unit, is defined as the ratio of total transfer coefficient times the surface area over the C minimum. As you can see, this ratio correlates the heat exchanger design, which is the surface area in the numerator. So what we need to have is we need to have a correlation between the effectiveness and the NTU. So as you can see, if we have this correlation and we know the operation conditions, which are the effectiveness, then we can calculate the NTU and then calculate the surface area. That will solve a design question. How much surface area we need to design in order to achieve the Q that we need, right? And then on the other hand, if we know if we know everything about the heat transfer heat exchanger and also some conditions, and we know this NTU, as you can see, the surface area we know, the convection coefficient we know, and the C minimum we know, and then we can know this NTU, and then with this correlation we can calculate the effectiveness, and then we can evaluate how much heat this exchanger will allow us to do. That's a performance of the heat exchanger. So what we need is actually we truly need this correlation between these two. And once we have that, we can solve the equations. We can solve the problems. And then these are the two tables, what we're going to discuss in the class. And then basically the first table is to calculate the effectiveness. So if you look at the table, it's basically effectiveness equals to certain function of the NTU. And then in other words, if you know the NTU, you look at the first table and you get the effectiveness. And then the second table is reverse. Once you know the effectiveness, then you can calculate how much NTUs you need for the exchanger. And then for each table, there are different categories. So the first one is the concentric tube shell exchangers. And then second one is the shell tube one pass multiple passes heat exchanger. And then the third one is the cross flow heat exchanger. And the last one is actually extreme case where the C equals to 0. And by the way, C equals to 0. C here is C relative to C. C is the ratio between the C minimum and the C maximum. So if you look at this ratio, if C equal to 0, that means C maximum is infinite. Sorry, equals C maximum is infinite. C maximum infinite means there's one fluid has a large amount of flow. In other words, it's excessive amount. The temperature of that fluid will not change. So that will basically to one of these cases that we discussed last time. So this will be the hot fluid will be infinite amount, and this will be the cold fluid infinite amount. In either cases, the ratio between the two will equal to 0. And then that will be a special case when we calculate the effectiveness and the NTU. All right. In the class, we will use example problems to solve the evaluation and the design questions.